Hello once again, and thank you for joining us. This is Space Nuts. My name is Andrew Dunkley, your host. It's great to have your company. And as this is the 360th episode, like we do every fifth episode, it is dedicated 100% to audience questions. We will be covering black holes, strangely enough, exoplanets, exoasteroids, time dilation, redshift, the balance of power in the space race as it stands now and what we think about that, and metallicity, all coming up on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Yes, and joining me to answer all questions known to mankind is Professor Fred Watson, astronomer at large. Hello, Fred.
It might be not just humankind, but it might be alien kind as well.
It could be, yeah. There's all sorts of possibilities, indeed. But yes, how have you been?
Not so bad, thank you. My nearest and dearest has got the most awful cold, so I expect it'll come to me soon. Who knows what state I'll be in next time we speak.
Yes, well, fingers crossed that you managed to avoid it. My dad's got it at the moment too. I was down Newcastle Way to celebrate my brother's 60th birthday last week. So he co-hosts with Tim Gibbs Astronomy Daily. So, we had a good time. It's nice to catch up with family. And I played golf in the most brutal wind known to mankind or humankind last Saturday. I don't know if it was windy in Sydney. I imagine it was, but
horrendous.
Gosh, it'd blow the dog off a chain. And I played golf in it at a lovely course called the Vintage in the Hunter Valley. Right. A course I've always wanted to play, very challenging. So why don't we make it harder and play in a 40 mile an hour
I
wind?
think it was one of your balls that ended up in our back garden, actually. Here in Sydney.
It probably did, yes. Yes, it was a northwesterly, so it could have gone your way. But, it was brutal out there, absolutely brutal. But I actually played quite well despite the conditions. But,
very good.
Yeah, lovely, lovely part of the world. Wow, what a golf course. Gosh. Walked into the locker room and thought, oh, gee, I don't belong here. This is way too out of my league.
There are places I go to that I feel like that about as well.
Yeah. All right, let's get down to business. We've got a bunch of questions from our audience who stick with us regardless of what the reality is. But let's go to one of our regulars, and that is Rusty from Donnybrook.
Hey guys, it's Rusty in Donnybrook. Well, here we are. We're at aphelion and midwinter, and we're having some of the coldest mornings I can remember. But I hope you guys are keeping warm and you're keeping well. In June, on the 22nd of June this year, there was an integrated metallicity profile of the Milky Way published in Nature Astronomy. And one of the findings was that the peak metallicity in our own galaxy is at about 25,000 light years from the galactic centre. It trails off again shortly after getting to our distance, which is 26,000 light years, to be very low, about a third of the metallicity of our own sun by the time you get to the edge of the galaxy at 50,000 light years. So I'm just thinking about the Drake equation, and it would seem that a metal-rich locality would be one of the things that complex life like ours is in need of. So it might be a good place to start looking in other galaxies, not this particular distance, because I believe it changes from galaxy to galaxy. Anyway, what do you think? Cheers.
Thanks, Rusty. Yeah, that's a good question. And, of course, we are looking for signs of civilizations elsewhere. We're looking closer to home for signs of life too. But I suppose we have talked in the past about places that look more likely than others. Has Rusty got a point with the metallicity theory?
Yeah, and indeed it's well built into, the interests of astrobiologists looking for signs of life on other worlds. So just to give the backstory here, metallicity it's a measure of the extent to which metals are present in the atmosphere of a star. And by metals, astronomers mean everything other than hydrogen and helium. Hydrogen and helium aren't metals, everything else is. So oxygen is, carbon is. It's a different definition from what chemists call metals. So a metal for an astronomer is pretty well anything you like. But all of that.
Let's just keep it simple. We'll call everything metal.
And in many ways, there's a good reason for that, because hydrogen and helium were formed in the Big Bang. So they are primordial. They've been there since the beginning of the universe. But the other chemicals haven't, the other elements. They've been formed in the atmospheres of stars through many, many generations of stars in our universe. And so with each new generation, the metallicity is enhanced. You generate more metals, i.e. things other than hydrogen and helium. When that star either explodes or turns into a planetary nebula or whatever at the end of its life, it essentially enriches the interstellar medium. That's the very, very, very rarefied gas between the stars. It enriches that with higher metallicity compounds. So metallicity is a measure of how much metal there is in a star's atmosphere, and normally you do it, and indeed this is exactly what's quoted in the paper that Rusty referred to. You normally do it by looking at the ratio of iron to hydrogen in the atmosphere of the star. That's termed the metallicity, and it's effectively zero for. It kind of calibrated to be zero for solar type stars like the sun. So things that have got more iron in them than the sun will be said to be metal rich. Things that have less iron would be said to be metal poor. And I think Rusty's reasoning is correct, that it's probably a consequence of the fact that we are a planet of a metal rich star that gives the Earth all the different kind of chemical elements that we need to form life, particularly carbon, oxygen, hydrogen, nitrogen, a bit of phosphorus, and those other things that living organisms seem to need. So you would naturally look for metal-rich stars if you are looking for planets that might host life. And so, I think Rusty's comments are on the money. So in a sense, it's, he's pointed out this Nature Astronomy paper, which indeed shows that the metallicity in our galaxy, among stars in our galaxy, and there are about 400 billion of them, so there's plenty to choose from. But what you can plot a curve that shows how that changes with distance from the galactic center. This is exactly what Rusty's talking about. And it peaks more or less at the solar radius where we are. And that's very useful because they're the nearest stars to us. And those are the ones that are easiest to look for exoplanets or to look for biomarkers in their exoplanets. We're only just starting to do this by analysing the atmospheres of exoplanets. And the James Webb Telescope has been successful at some level with that. We've found, you and I have talked about, I think sulfur dioxide was the most perhaps exotic compound that's been found by James Webb Space Telescope in the atmosphere of an exoplanet. So that's where we're looking. Rusty makes a comment, should we be looking at this same radius in other galaxies? And I think he's right that the metallicity gradient the profile doesn't necessarily follow what we have in our own Milky Way galaxy. But the problem with those stars in other galaxies is they're very difficult to observe because they're a long way away. We can, and I think there is one example might be two of an extragalactic, in other words, outside our own galaxy, exoplanet, in other words, outside our own solar system. I think there was one picked up in Andromeda, in the Andromeda galaxy a while ago. There might be more.
Okay.
But it's certainly good news for our own galaxy. And very briefly, Rusty mentioned aphelion at the beginning, which is the time at which the Earth is at its most distant from the sun. It coincides with, I think it's the 3rd of July is usually when it is, if I remember rightly. But I always used to feel when I lived in Scotland, where in January it's freezing cold and pretty miserable, and yet we are nearest to the sun on the 3rd of January, which tells you that the distance of the Earth from the sun doesn't actually make too much difference to the climate. It's all about the tilt of the Earth's axis and the seasons.
Well, I think I read the other day that June was the hottest month on record globally. And yet we were freezing here.
Well, that's right. Yes, we are in the upside down part of the planet, so we've got to put up with things like that.
we do. Okay. Thanks, Rusty. I suppose the question would be is if we were going to be looking for potential life regions in Andromeda, we could analyse the stars there and see where the peak point is.
I'm sure that's been done because the stars in Andromeda are well observed. I haven't got a reference to that in my head, but it's an interesting thing to look for, so we should do.
Yeah, it would be. Yeah. Okay. Thanks, Rusty. Good thinking. Before we move to the next question, for those who are not TikTok users, we do a promo every week on TikTok before we record the show proper. And we usually end it with a dad joke. Unfortunately, it's starting to catch on. This comes from Misty West, who's one of our regular listeners and contributors occasionally. Where do bad rainbows go, Fred?
Wait a minute. Bad rainbows.
He's got a good run at solving these.
I'm not sure I'm going to get this one, though.
Well, I'll put you out of your misery. Where do bad rainbows go? Prism. Wait for it. It's a light sentence and gives them time to reflect. That's
like
pretty
that
good.
Very much. Yeah.
That is very good. Okay. Let's move on to our next question, which comes from Russ. Guess what it's about?
Oh,
no introduction needed.
Right.
Hi, Fred and Andrew. It's Russ here from Stylebridge. Love the show as always. And I have another question about black holes, which I'm sure you're delighted to hear. It is related to our universe. Apparently, according to scientific discoveries, if you took all the matter in our universe and you compacted it down so it created a black hole, the event horizon would be larger than our visible universe. Also, there is, as we look out into space further and further, the space is expanding quicker and quicker. We get to a point where it apparently exceeds the speed of light, which would mean that light could not escape. Does this mean that we are living inside, as has been speculated, a giant black hole already? What are your views on this? I'd love to know. Thanks a lot.
All right. Thanks, Russ. Bye. Let's hope all the black holes in the universe don't decide to have a convention soon, if that's the case.
Yeah.
It could be dark.
It would be dark. Yeah, it would be very dark. Look, I actually find that hard to believe, that the event, if you combined all the matter in the universe into a black hole, maybe it would. Maybe the event horizon would be comparable in size with the universe,
or the visible universe.
That's right.
Yes,
that's right. That's the tricky bit, because the universe may be infinite. That's the really, that's the snag with all these discussions. But it's been the idea of are we living in a black hole has within a black hole event horizon has been around for quite a long time. It probably goes back to the likes of Roger Penrose back in even in the 90s, 80s and 90s. So I've never really got excited by this idea because I think it just adds a complication to something that's already really complicated. And in terms of the light being stopped because the universe is expanding faster than the speed of light and things of that sort. Yes, we do know that happens, but I don't think you need a black hole event horizon to postulate that. So I'm not big on the idea of the universe being that we are within the event horizon of a set of massive objects. But who am I to complain if people come to the conclusion that that's the case? I saw an interesting headline in New Scientist. I didn't read the article, but I just saw the headline as it went past, which was, is the entire universe a quantum object? I think that's what it was, something like that. So are we all completely entangled with each other? And, well, you can take that question on many different levels, can't you?
Yeah, you can, and it just makes people's brains hurt, particularly mine. But not likely that we're all
I don't think so.
in a giant black hole.
Yes, I'd like to sit down and read some of the detailed discussions of this, which I have to say I've never done. I've just thought, look, that's too hard. It's bad enough trying to understand what's in the universe already without throwing in this idea. I'm not a cosmologist by training, although I've worked a lot with cosmologists because I've built instruments that provide them with the data they need, and indeed manage surveys that provide them with the data they need. But the stuff that they do with them is quite mind-blowing.
I worked with a cosmologist once because it was his nickname, because every time you asked him a question, he'd or asked him to explain something, he'd say, because.
That's a bicosmologist, though, isn't it? Not a cosmologist.
Yes, that's right.
Bicosmologist.
Yeah. A cosmologist, yes. Because.
You should have saved that for the dad joke, actually.
Well, the problem is because when we record, we go out live sometimes, they're coming in thick and fast. Okay. Misty is really thrilled that she achieved her one and only chance to stump you, Fred. So.
I do like I like the prism idea, though.
It's a good one. Okay, from black holes to black holes.
Okay.
Hello, Andrew, Fred and Hugh in the studio. This is Petrus here in Auckland, New Zealand. I'm going to bring up an old chestnut question about black holes. And it's something I just can't get my head around with black holes. I get the whole mass of a black hole, like they can calculate the mass of a black hole by the gravitational influence of the surrounding space and the size of the event horizon and all that kind of stuff. I get that. Well, I think I get that. What I don't get is when they say a black hole's got no size. But how do they know it's got no size? They've already established that the regular laws of physics don't apply when it comes to black holes, and nothing can escape from a black hole, not even light. So nothing can escape from that event horizon. So it's impossible to image anything from within there. So how do they know there's actually got no size? How do they know there's not a ball in the middle of that gravity well, the size of a football or the size of a golf ball or something like that? And how do they know it's got no size at all? That's basically my question, and I hope I don't get even more confused by the answer. But thank you very much.
Thank you, Petrus. I think what you'll find in a black hole is an object the shape of a pen, because they've got to go somewhere.
It could be the shape of one sock as well.
It could be. Yes, that's a thought. That's a definite thought. But when we talk about black holes, we do actually assign sizes to them: supermassive black holes, intermediate black holes, etc. So we do know that there are various sizes, but I'm thinking he's talking about a different element of the black hole theory.
Well, yes. So Petrus mentions that they come in different masses, but it's the physical dimensions that's at issue here. And I think he's actually right. I think he's on the right track because whilst the formal definition of a black hole, at least as I was taught it, is a point in space with infinite density, that suggests that if its density is infinite, that its dimensions are zero because it's got mass. Mass is density is mass over volume. So if you have zero volume, it doesn't matter what the mass is, it's going to have infinite density. So that's a formal definition. But I have read articles and papers which talk about black holes actually having physical dimensions. In other words, their density is not quite infinity. It's nearly infinity, but not quite. But they still show the properties of black holes. And actually, the other thing that plays into this is that the black hole properties are varied. In between, for example, a rotating black hole, which has quite different characteristics from a non-rotating black hole, and you don't need to look very far on the web to find numerous accounts of these different things. Rotating black holes, I think they're called K-E-R-R black holes. I should know all this, shouldn't I? It's a long time since I looked at it. There was a point I was going to make. Yeah, that's right. There is another aspect of black holes, which I like very much. It's called the no-hair theorem, which I wrote.
Be careful, Fred.
I wrote about in one of my books, and I can't remember anything about it. No, the no-hair theorem says that there are only certain things that you can detect about a black hole. And I can't remember what they are, like charge and mass and things of that sort. But I really need to revise the no-hair theorem. It will be very easy because I can't remember which book it's in. I think it's in Cosmic Chronicles. I wrote about the no-hair theorem, simply because I quite like the idea.
So, what was the answer to the question?
I think the answer's. Petrus is right, that maybe some black holes do have physical dimensions because they're not quite fitting the formal definition. That's the thing that I would look for, and I probably will. I'll go and have a look for it just to check whether I'm talking complete rubbish. But I think I do recall reading about black holes which are not infinitesimal in size. In other words, just to tie up the loose end here, they're not a singularity, because that's the point about a point with zero dimensions. It's a singularity. It's a twist of space.
So, most of them are, but some of them aren't.
Maybe. Or maybe most of them aren't, but some of them are. Yeah, it's a great question.
All right. Thank you, Petrus, for your question. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Okay, Fred, we might as well just keep on churning through our questions. The next one comes from Mikey.
Hey, Fred. Hey, Andrew. This is Mikey from Illinois. Hope you guys are doing well. And so here's my question. When we watch an exoplanet pass in front of another star, say 500 light years away, are we seeing that planet pass in front of its star 500 years ago? I'm assuming the answer is yes, but this popped into my head this morning while making today's coffee, and I just never considered it before. Can't wait to hear the answers, guys. Thank you so much. I absolutely love the show, and thanks for always giving me something to look forward to.
Gee, you must be desperate, Mikey. But anyway, appreciate it. And it's funny what pops into your head when you're making coffee. I would suspect the answer is yes as well, Fred, because everything we see is historical.
That's correct. Absolutely. So, yeah, the planet passing in front of its parent star, that happened 500 years ago, and hopefully still happening now, but we don't know. And because absolutely everything in the universe, no matter what we observe, we're looking back in time. We tend to we tend to ignore the actual physicality of what's happening. The fact that in our time frame now that planet is still going around its parent star, but we're only seeing it as it was 500 years ago. That has no relevance in astronomy. All we can learn about or make any reference to is what happened at the look back time. That you're looking back 500 years. So, if it's a 500 light year away star, so yeah, that's the answer.
It's hard to get your head around, but you could be looking at a star and it doesn't exist anymore because it's so far away. It's we're seeing it. Who knows how many thousands of years later, possibly longer, and it might well have destroyed itself by the time we've seen it. But we're seeing it.
Yes,
historically.
that's right, and there's no way. So what I was trying to say before, it's all about causality as well, because cause and effect can only take place at the speed of light. So there's no, the fact that, yes, for example, if that star 500 light years away had detonated into a supernova, that radiation that would come from the supernova hasn't reached the Earth yet. And so from our perspective, that star is still there. But eventually we would recognize that, no, it's not still there because it's just blown up. It blew up, however many hundred years ago it was. So it is to particularly people coming fresh to astronomy. It's slightly odd concept that we're always looking back in time, but we are. Just one nuance to that, though. If you've got an exoplanet going around a star that's 500 light years away, yes, when the planet's on the backside of the star or behind the star, its distance is slightly more than it is when it's in front of the star, and that's reflected in the light travel time. So there is a slight correction that you would need to make and these corrections are made when people observe these exoplanets for the different light travel time from when the planet's behind the star to when it's in front of the star. And in fact, it was that process, not with exoplanets, but with Jupiter moons, that led an astronomer called Römer in the 1670s, I think, to work out what the speed of light was in Denmark. Danish astronomy.
There you go. Yep. All right. Thank you, Mikey. We'll go from Mikey to Michael.
Hey guys, this is Michael. I'm from Toronto, Canada. It's my second question to the podcast. A feature of science is that new breakthroughs can lead to major revisions of our previous best theories. We've seen this time and again over a few millennia, say where we've gone from geocentrism to the discovery of the cosmic web and everything in between. Could we be at such a turning point now, thanks to observations from JWST having ostensibly found galaxies that are too mature to be explained by the Big Bang? What if rather than the Big Bang, we had massive supernova of population 3 stars, which are hypothetical and I don't think they've been observed yet? Could this have given us the same evidence that we instead credit the Big Bang with? Maybe we're engaging in underdetermination of theory by data. Or could there be evidence that these galaxies we're observing from far back are galaxies of population 3 stars themselves, but because we don't know enough about the way these stars evolve, it's thrown off our models of what the early universe and early galaxies looked like in an earlier epoch. Thanks, guys.
Wow, Michael, that is deep. That's so deep. I don't think light's penetrating.
Well, I think Michael's question is a great one.
It is.
So, yes, the James Webb Telescope has shown us galaxies that are more evolved than we would expect for their age, for the age of the universe as we see it at that time. But that doesn't mean that we've got the basic paradigm of the Big Bang wrong, because it's supported by so many other, observations like the cosmic microwave background radiation. The whole deal suggests that we are on the right track with the Big Bang. There are some nuances. We get 2 different values for for the current expansion of the universe. It's what's called a cosmological tension, because when you look at the expansion of the universe as measured today and as measured from galaxies around us today, compared with what you get by measuring the cosmic microwave background radiation, the flash of the Big Bang, you get two different answers. They're about it's something like 5% different. So that's something that when I started work in astronomy, people would have been delighted to get an error of 5% because the errors were more like 100% back in those days. Anyway, I think, however, Michael makes a very good point with the idea that possibly we are underestimating things like the influence of population 3 stars, about which we don't know. What are they? Population 3 stars are the first stars to form in the universe, where all they had was hydrogen and helium. None of these metals that we were talking about a few minutes ago had come into existence. So they were the first generation of stars. And, it may be that their influence on galaxy evolution is something that needs revised. I don't think we're going to push back the date of the Big Bang any further. I think that's pretty well understood 13.8 billion years ago. But our understanding of the earliest galaxies, the first galaxies to come into being, is based on theoretical ideas that may well need changing because of new observations. So I think Michael makes a good point.
He does, whatever he said. Yeah. I love the way people really think about some of the mysteries and things that we're trying to unravel in astronomy and space science, including a question without notice that's come in due to our live casting of the recording session. Here it is. It's from Emil. Has a question about how fluids work in the human body in space, like stomach fluids and blood and all that sort of stuff. What happens in 0G with all your bodily fluids? I certainly know what happens in 1G, and I don't like it.
Yeah, they do. That's right. Well, this is the one of the key pillars of space medicine, I guess. It's one of the things that really people had to struggle with when humans were first going into space. So the heart does all the work. You don't have gravity to help you, and that means that you need to keep your cardiovascular system in really good nick, and that's why they all do a couple of hours on a treadmill every day or on a bike or whatever when they've got long periods in orbit. So I think it's pretty well understood from a medical perspective just how these fluids keep on going round. You do want, there are aspects, I guess, that like the way our digestive processes work, they tend to need help from gravity because everything's going downhill. But when you think of many animals whose digestive processes are taking place horizontally, well, it still works. And so that would suggest that gravity is not playing that important a role in that. But as I said,
I think that
it's well understood science.
Yeah, the fluid in the eyes is one of the more critical areas of worry.
Yes, with eye pressure and things of that sort. That's it.
Yeah.
Good stuff.
Yeah, good question. All right, another one. This comes from Josh.
Hey, Andrew and Fred. My name's Josh from Sydney. I'm a long-time listener, first-time question asker. I absolutely love the show, so thank you both so much for producing it, putting it online. So my question is about the conservation of energy and the redshifting of photons. So when we look at the cosmic microwave background radiation, as the universe is expanding, those photons are getting redshifted, but that also means that they're losing energy. So where does that lost energy go? Because it has to be conserved, right?
Okay. Thank you, Josh. Redshift is starting to become a popular area of inquiry. I'm finding we've been getting a few questions about it lately,
and it's the probably the pillar of our understanding of the wider universe is redshift as well. It's very important. So Josh is absolutely right that a redshift represents a loss of energy. Now, I followed up on this once, possibly because of an earlier question, or it may have been a question on a radio show. I did follow up on that, and I think the answer is, it sounds
42. No,
it's worse than 42. It contributes to the overall energy of the universe itself, if I remember rightly from my reading on this.
Okay.
Because Josh is right, energy is conserved. Photons are losing energy, and it's tempting to say, well, it contributes to the expansion energy of the universe, but that's a sort of circular argument, and I don't think it can be that. But I will check on it again. I do remember exploring this idea in some depth, but it was so long ago that I've forgotten the details. So it does go somewhere. That's the bottom line. It does go somewhere. It probably goes into that cup of coffee that was it. Can't remember who was making it. one of our listeners.
I think it was Mikey.
That's right, Mikey's cup of coffee. So yes, but Josh is absolutely right that redshifting is a loss of energy from the light, or it's a change in the energy of the light, and it does go somewhere. Warms up the universe. That could be the bottom line.
Once again, we demonstrate our prowess for giving you adequate
I don't
answers.
think that's anything like adequate, Andrew. I'm embarrassed to be here. I think most of our listeners know more than we do.
Yes, and then they ask us questions about it.
I think that might be the whole thing. Here's a conspiracy theory that the whole reason why Space Nuts is there is to make our listeners feel more intelligent because they are.
Yeah, it's working. All right. Thanks, Josh. This is Space Nuts, sort of, with Andrew Dunkley and Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Okay, we'll cram a few more questions in before we wrap it up. The next one comes from DJ.
Hey, guys. This is DJ from Indianapolis, Indiana, in the United States. My question is about time dilation. I've heard it said that one way that you would be able to see the dilation would be if a spaceship is traveling past Earth and you can see into it, like through a window, and you would see that clock. And the spaceship that's traveling close to the speed of light, you would actually see it tick slower than yours. Since our second is no longer determined by the speed of the Earth, but by the cesium atom electron spin, does that change as well? So if you're in a spaceship going the speed of light and that cesium atom electron spin is 9 billion whatever times a second, does it now spin at 4 billion times a second or 2 billion times a second if you're going close to the speed of light, or does it not know the difference? Hopefully that was clear enough to get an answer. I really enjoy the show. Thanks, guys.
And welcome to our world, DJ. You might want to explain what he means by the way we've changed the definition of a second.
Yeah, so a second's defined in atomic frequencies. It's gone from we've known for many years that the Earth is a pretty poor timekeeper in terms of its rotation, because the rotation changes. So if you're going to define a second as being 1/3600th of an hour and an hour as 1/24th of a revolution of the Earth, then it's going to change over time. So it's been defined in terms of I'm not sure whether it's still defined in terms of vibrations of a cesium atom, but it certainly used to be. But here's the thing, though, in terms of the relativistic time dilation, that as far as the cesium clock in the spacecraft is concerned, it's still vibrating at the same rate. It's that an observer who's in a different reference frame sees it basically vibrating slower. And that's how it would look if you could see the vibrations of a cesium atom in a passing spacecraft. They would look to be slower because time is taking place more slowly, apparently. But for the people in the spacecraft, it's still the same. Nothing changes.
We talked about this last week with someone questioning the gravitational effect of a black hole with people on a planet in the movie Interstellar, how they portrayed that 7 years pass for every hour, which was an extreme example. But also, if we were in a different place in the galaxy and we could observe people in another part of the galaxy, they would either look like they're moving faster, like an anthill, or slower, depending on which part of the galaxy you were in and the time dilation effect.
Yes.
Is that right? If you could observe them in real.
This is we're now talking about gravitational time dilation, and rather than the velocity time dilation, which is what DJ was referring to. But the two effectively are the same.
I always get those two mixed up.
Well, shame on you, Andrew. So the issue is that it's always about reference frames. It's about how you see, how you in one reference frame sees somebody else and other things going on in a different reference frame. So that, yes, if you were at a different point in the gravitational well, you would see time progressing at a different speed, and it would depend on where you were in the gravitational well as to whether that was faster or slower, exactly as you've said.
Perfect. All right. Thanks, DJ. The next question comes from Colin.
Hi, this is Colin from Abilene, Texas. And in your last episode, you had researchers say they calculated the trajectory of the comet or asteroid that was outside our solar system. But couldn't it have just as easily come from the Oort cloud because it surrounds us in the sphere? Thank you.
Thank you, Colin.
I enjoy the show. Appreciate it.
We do too. Thanks, Colin. I think we can dismiss the Oort cloud theory because of the speed of these particular things.
So you don't need me. You don't need me, Andrew. You don't need me at all.
I'm just remembering what you taught me, Fred.
Yeah, that's right. So Oort cloud comets come in at certain velocities. I can't remember what the maximum is for an Oort cloud comet, but
Fred, wait for it. You ought to know. Thought that was a good one.
Yeah, I like that one. You ought to take notice of the Oort cloud. Yeah.
Yes.
Anyway, never mind. Jan Oort was a very, very competent astronomer who did a fantastic amount of interesting science in the early post-war years, post-Second World War years. Anyway, that's all about. So Oort cloud comets come in from the Oort cloud at velocity x, but something interstellar would come in at 2x or x plus 50 kilometers per second or something like that. They're much faster. So that's the critical difference between, an exo asteroid perhaps or a comet or an asteroidal body that's come down from the Oort cloud. So it's all about it's a matter of degree, I think.
Yeah. If an exo asteroid just happened to impact something in the Oort cloud and sent it hurtling our way, you'd still know the difference, wouldn't you?
Yeah, you probably would, actually, because I mean, this is along the lines of the theory of that object that we were talking about last week, that it may have been disturbed by Planet 9, had a gravitational tug by Planet 9, but it's still coming in at an excess velocity. That's correct.
All right. Very good. Thank you, Colin. Lovely to hear from you. And we've got our final question for this week from Andreas.
Hi, Andreas from Sweden here. Thanks for a great podcast. So I have a question I would like to get your input on. As we can all feel, the world is kind of moving in a direction of having two major space power blocks. Like on the one side we have the US and Europe, and on the other side we have China and Russia. So, which kind of brings back the feeling of the old space race, between the US and Soviet Union, which propelled things forward a lot. But if we look from the perspective of humanity, do you believe having these two competing blocks is better than if we all came together as like a one happy space family reaching the stars together? So what do you think is better for scientific progress and exploration? Is it collaboration or competition? Thanks. All the best.
Great question, Andreas. As a matter of fact, he's forgotten North Korea. I just finished watching season 3 of For All Mankind, and they were the first to step on Mars.
Okay.
So,
okay.
Hope that wasn't a spoiler for anybody. Good grief. Sorry. Block your ears. Too late. The space race has changed. It used to be the US and Russia or the Soviet Union, and now it's the USA, Europe, and Russia and China, although they do tend to work independently, they do collaborate. But what we are seeing is that we've got collaboration from just about all and sundry, maybe to a lesser degree China, but they're not completely blocking everybody out. And one would hope, and we do see this a lot in astronomy and space science, is that they do share data, they do share information, they do share resources, they work together. So I, from my perspective, I think it's good the way things are going at the moment. What worries me is that someone will get somewhere or find something and say, "Well, no, we're not going to share that. We're going to mine the hell out of it and keep it for ourselves." I don't know. I'd rather it be a cooperative venture than one of conflict, although conflict has also proven to be the mother of invention in the history of humanity. So cut both ways as far as I'm concerned.
That's Andreas's point, isn't it? That we gained enormously in the 1960s by that geopolitical competition between the Soviet bloc and the Western bloc, in particular between Soviet Union and NASA. So, but I do think you've got to kind of bring together. There are a number of ways of looking at this. Maybe space can be a beneficial thing in terms of international relations rather than in terms of technological development. So you're still seeing, I suppose, the last vestiges of that with the International Space Station, which still has Russian and American astronauts and cosmonauts basically collaborating in a fantastic way. And so space diplomacy, I think, still has a place in the world's future. And I've often wondered whether, yes, there's certainly competition at the moment, and a lot of that is to do with the rise of China, the fact that you have a nation here that wants to assert itself as a world player on a world stage with a different geopolitical system from what the Western world has, and that is perhaps one of the reasons why we're seeing such really capable and quite notable achievements from the China National Space Agency Administration, CNSA. I think perhaps looking further into the future, when we're talking about flights to Mars, human exploration of Mars, I suspect that will turn out to be so expensive that the only way we'll really make it work effectively would be to have international cooperation. And it may well be that we might see a new era of warm and fuzzy international cooperation, perhaps comparable with what we saw around the time of the end of the Cold War.
That said, though, the war in Ukraine did lead to space tensions between the US and Russia. but it was something that was happening on Earth that caused that. And I'm pretty sure the people that were in space at the time really didn't want to have a bar of it, but they were following orders.
Yes, that's right. I can't remember whether I mentioned that when I was at the Committee on the Peaceful Uses of Outer Space, that meeting in February, that those geopolitical tensions were very, very evident in some of the comments that were being made by, delegates of certain nations, and it was all about the war in Ukraine. So when you've got something like that going on, then it really clouds the issue. But all credit to astronauts, cosmonauts, for sticking together up there in the International Space Station, and to their respective space agencies for actually negotiating diplomatically. Roscosmos had a firebrand head who's now been removed. He's now in Ukraine, actually.
Yes.
Dmitry Rogozin, was that his name? I can't remember.
Yeah, that sounds about right.
He's so, and we've had far kind of fewer belligerent signals from Roscosmos since then, although, the internal politics might be the same. But we've got, still in the space station itself, it is business as usual, which is quite extraordinary, quite extraordinary.
It is. It seems in terms of space exploration and even, being close to home, orbiting in the International Space Station, they tend to leave the politics to the politicians, and up there, away from it all, it's a different world, and they all get along most famously much of the time, as far as we're aware. And
that's right.
Yeah, and I hope it stays that way. And yeah, I hope you're right about the future of exploration to Mars. Maybe it will require international cooperation, and to make it happen, bring everybody together. I think that would be a great thing. Thank you so much, Andreas. A fantastic question. We don't usually get into politics, but that was a good one. That brings us to the end of the show. Of course, if you do have questions for us, you can send them through our website. The AMA tab or the Send Us Your Voice Message tab is the way to go. You can send us text questions as well. Don't forget to tell us who you are and where you're from, and peruse the Space Nuts shop while you're there. There's nothing worth buying, but do it anyway. Thank you, as always, Fred. It's been a great pleasure. Great to spend some time helping people understand space and everything, and although half the time they help us understand a bit more too.
That's right.
It's really good. Thank you, Fred.
Pleasure, as always, Andrew. Look forward to speaking next week.
We will. And thanks to Hugh in the studio for sending messages through from our live audience while we were recording today. Oh my gosh, I said something nice about Hugh. That won't happen again. And from me, Andrew Dunkley, thanks for your company on this edition of Space Nuts. Catch you on the next episode. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.